So as we have discussed, the alkylation process is improved for the octet number. So here we can see the diagram for the alkylation process. So here you can see the feed which is mixed with the sulfuric acid and the other components, and then the caustic is added to maintain the pH. Then the dark line, it will show the product stream. So isobutane and alkane, they are generally used to get the alkylation. So that will react and they will give the alkylate as the final products. So here the reaction as settler, they are shown in the diagram. So here they will react with the alkanes, and we will get the branch alkane or the alkylate in the product, and then it is through the caustic scrubber, the caustic is removed, and then the alkylate and the other products which is propane and butane, which is low molecular weight, they will be removed from the stream. So generally de-isobutanizer is there to remove the isobutane from the product. So alkylation with the sulfuric acid in Statco contactor with octo-refrigeration. So here what happens, the alkyne isobutane feed is fed in the reactor, it is well mixed, and then reaction is allowed to take place. Then emulsion, which is of hydrocarbons and acid, it is sent to the settler, and reaction acid is recycled back. The alkylate, which is C3 plus C3 compound, they are removed and then sent to the condenser and separator, and then recycled C3C4 is added in order to have the alkylation. So the PC, it will control the pressure level and it will allow the reaction to take place incompletely. So conversion of heavy residues. So here the packing of light crude even in a complex refinery with fluidized catalytic cracking, hydrocracking, etc. does not yield a satisfactory product distribution. The amounts of fluid are too high. So hydroskimming refinery and complex refinery, if we say, so the majority goes in the gasoline. So hydroskimming refinery and complex refinery. So if we compare both of them, then gasoline percentage is very low in this one, and kerosene percentage is also low. But in the case of complex refinery, we can have the more of the gasoline and kerosene content, which is desired for the market conditions. So for heavy oil, the situation even worse, with 50% for oil being produced even in a complex refinery. So we have to go for the procedure where heavy oil we can crack and we can make more of the petroleum. If fuel is worth original is less than the original crude, so this is the major problem. The value of the products decreases in order. Gasoline is highly demanded, then comes kerosene, then crude oil and the fuel oil. So it is shown that fuel oil is not at all desired. So measures are done in order to decrease the fuel oil. So here the some of the things is achieved, and we are reduced from 65% to 47%, but still the 47% we have to consider about. So there are several reasons for an increased incentive to convert fuel into lighter products. The demand for lighter products such as gasoline and automotive diesel will continue to increase while market for heavy fuel oil is declining. Environmental restrictions become more important. Fuel oil contains high amounts of sulfur, nitrogen, metals, so measures must be taken to lower emissions. With the exception of Western Europe, the quality of crude oil shows a worsening trend. It becomes heavier with higher amounts of petroatoms, so more extended processing is required to obtain the same amount and the quality of the product. In principle, there are two solutions for upgrading residuals for obtaining a better quality distribution. These are carbon out and hydrogen in process. Example of carbon rejection process are the flexi cooking process by Exxon and the FCC process discussed earlier. The example of hydrogen addition process are the LC finning process by Linus and the Hacon process by Shell. So fluid cooking and the fluid flexi coking that we'll see. So both fluid coking and flexi cooking use fluid bed technology to thermally convert heavy oils such as vacuum residue, atmospheric residue, tars and bitumen, heavy coal fluids, these filter bottoms or cat plant bottoms. Flexi coking goes one step further than fluid coking. In addition to regenerating clean liquids, flexi coking also produces a low BTU gas in one integrated processing step that we can virtually eliminate petroleum coke production. The advantages are flexibility to handle a variety of feed types, high reliability with the average service factor between 90 to 95%, large single train capacity provides an economy of scale that lowers investment costs, able to process 65 kb per LD of 28% contracts and carbon resid in single reactor. Time between turnaround certainly approaches 2 years, able to process very heavy feedstocks such as de-asphalter bottoms at high feed rates. Additional flexi coking benefit integrated gasification up to 97% of gas coke. The fluid coking distillate conversion process uses non-catalytic thermal chemistry to achieve high conversion levels with even the heaviest refinery feedstock. Since most of the sulfur, nitrogen metals and condensed carbon dioxide fuel contaminants are rejected with the coke, the fuel range of our products can be filled for an FCC unit. Use as a single train reduces manpower requirements and avoids process load swings and frequent thermal cycles that are typical of batch process such as delayed cooking. The configurations available with fluid cooking are extinction recycle, once through and once through with hydroclones. So here you can see simplified fluid cooking flow plan. So the reaction it will come, then different fractions are removed, then cold coke then is fed to the heater where the net coke and fluid gas carbon monoxide boiler is separated. So here we are trying to minimize the loss of the feed into the coke formation. In a flexi cooking process, is the thermal technology for converting heavy feedstock to higher margin liquids and producing a lower BTU gas instead of coke. The conversion of coke to clean fuel gas maximizes refinery yield of hydrocarbons. The carbon reaction process results in lower hydrogen consumption than alternative hydrogen addition systems. The low BTU gas is typically fed to the carbon monoxide boiler for heat recovery but can also be used in modified furnaces or boilers. Atmospheric vacuum pipe steel furnaces, reboilers, wastage boilers, power plants and steam mills, or as hydrogen plant fuel, which can significantly reduce or eliminate purchases of expensive natural oil. The small residual coke produced can be sold as boiler fuel for regenerating electricity and steam, or as a burner fuel for the cement plants. So this diagram shows the simplified flexi coking flow plan. The flexi cooking process that will include the feed is sent to the reactor at temperature, then is sent to the heater where the coke is delayed, then it is sent to the cyclone separator where coke fines are removed, then is sent to the venturi scrubber and the coke slurry is removed and the coke gases then is removed. Then if unconverted it can be recycled back or heated at higher temperature in order to get the more coke gas formation, and that's how we can use the heavy gas oil for the good purpose. Catalytic hydrogenation of residues. This is the hydrogen in route where we use the hydrogen. It serves two purposes: removal of sulfur, nitrogen, metal compounds, and the production of light products. Reactions are similar to those of occurring in hydrotreating and hydrocracking of gas oils, but there are two important differences. One is residues contains much higher amounts of sulfur, nitrogen, and polycyclic aromatic compounds, and second being the removal of metals which are concentrated in residual fraction of the crude, means that operating conditions are more severe and hydrogen consumption greater than for hydroprocessing of gas oils. And next was catalytic activation, or in other terms we can say the poisoning of the catalyst. So generally when catalytic reaction is taking place, the reaction take place on the active site of the catalyst. So when there is absorption, the reactant molecule they will absorb on the catalyst where the reaction will take place. After the reaction will take place, they will dissolve from the side surface, and the product which is formed we can remove. So there are other elements which can poison the catalyst, or they will block the catalytic sites. So when catalytic sites are blocked, so they are not available for the reaction, and being they are not available for the reaction, your reaction time loses, also the product formation is less, yield is less, and is the loss. So generally we have to take into account when feeding to the catalytic reactor. So always you have to remove the trace elements or other impurities which may harm your catalyst. So poisoning a catalyst is very general. So we have to go for the catalyst which will not be poisoned easily, or we have to remove the impurities from the feedstock so that they will not contaminate the catalyst. So deposition of metals causes catalyst deactivation. Basically all metals in the periodic tables are present in the crude oil, with major ones being the nickel and vanadium. At the reaction conditions, hydrogen sulfide is present and metal sulfides are formed. So the reaction scheme is complex but may be represented simply as nickel in porphyrin with hydrogen gives nickel in sulfide and hydrocarbons, and the vanadium porphyrin plus hydrogen gives the vanadium sulfide plus hydrocarbons. The catalyst is poisoned by this process because most of the deposition occurs on the outer shell of the catalyst particle, initially poisoning the active side, then causing pore plugging. So when we say catalyst, so there are two things: the surface area of the catalyst, also there are deep pores inside the catalyst, like the capillaries in the tissue paper or in the plants. So they are also like the capillaries inside the catalyst particles. So that will serve for the active sites, as well as they will serve for the increase in the surface area of the catalyst. So when this catalytic poisoning agent they deposit on the surface of the catalyst, and not only block the surface but also these capillaries. So in order there is a tremendous decrease in the surface area, and that led to the lower yield and the lower product formation. So reactor used for the catalytic hydrogenation. So there are three kinds of reactors that are typically used. One is fixed bed reactors that we have seen in the fluid mechanics lab. Then fluidized bed reactors that also we have discussed in the lab, which is also called as ebullient bed reactors. And third one is the slurry reactor. So if you see in the diagram, so the first one says the fixed bed reactor where catalyst is fixed. So gas and liquid they will come then distributed along whole the bed area, and they should be wet completely. So inert beads this will help the liquid to separate fully, and catalyst bed where they are fixed, then support grid in to support the catalyst and will not allow the catalyst to drop down, and product we can remove from the bottom. The next one is fluidized, where the fluidization takes place. So here the gas we are suspending, so the gas will not only circulate the material but also keeps the catalyst in fluidized form. So here liquid we are fitting from the top, then gas stream we are injected, and catalyst they will be suspended in the fluid, and the gas bubble is formed. So that all will lead to the good mass transfer and the greater surface area. So lesser the size of the bubble, more is the surface area, more is the mass transfer. And the third one is slurry reactor where the slurry will appear. So the viscosity, if we compare with the fluidized bed and the slurry, so slurry will have the different viscosity than the fluidized bed, and it is a fully packed with the slurry. So gas will rotate whole the material in the reactor. So catalysts again they are in suspension form, and gas bubble form they will help in the mass transfer. Then product which is formed that we can collect from the top. The LC finning process that we'll see. So here the feed will come through the heaters, then it is coming to the catalyst bed. So catalyst will added, then reaction takes place, and then we can remove the catalyst, which we can send for the regeneration, and we can use it back. Then it is heated around 700 to 740 and at very high pressure through the reactors to ensure the major yield. Then it is sent to the lower pressure separator where it will separate the lower molecular fractions and higher molecular fractions. And after the fractionation we can remove the products, and then lower fraction that we are sent they are recycled back. So here after the high pressure separator, the separation again fed to the main product stream in order to separate the any products. Then hydrogen rich gas that we are sending for the hydrotreating process, whereas the off gas which are not useful they will be sent back. The hydrogen which is we generating we can recycle them back if it is in purer form, otherwise we will separate them, and the hydrogen gas which is formed again we will feed to the reactor in order to get the hydrocracking. So the overall process meaning is to get the lower volume point mixtures that will have the high economic value and high demand in the market. So this was developed by Limus and uses fluidized bed reactor. So process with fixed bed reactor if you see, so residue film it will go through HM catalyst and wide pores, so HDI catalyst narrow pores it will go. Then metal content when is less than 25 ppmw, then it is go through the fixed bed. 50 to 100 then it has to go through fixed bed 3-fold catalyst system. For more than 100 moving bed bunker STM fixed bed ester catalyst. Greater than 100 it is the bunker SDM catalyst regeneration needed, and fixed bed and ester catalyst. So replacement of deactivated classes in the conventional reactor is not possible during operation. Depending on the metal content of the feedstock, barrier combination can be applied. So these are the different combinations that we can apply in order to get the more yield and to avoid the less volume production due to the catalyst poisoning. In the Haken process, fresh catalyst is added into the reactor. So when fresh feed comes, then catalyst added where the moving catalyst beds where the reaction takes place. Then catalysts which are unreacted or the excess they will recycled back into the reactor. Then it is sent to the stationary catalyst bed. Hydrogen is added. Then the cracked product or the hydrotreated product we can separate them. Unreacted hydrogen we can send back for the regeneration. Catalytic regeneration occurs like use catalyst, then sulfur remover, then extraction, then drying, and then classification. Then we'll have the regenerated class list. So catalyst regeneration is achieved by removal of metal sulfides and carbonaceous deposit, essentially by oxidation and by extraction of the metals. So processes with the slurry reactors. Slurry processes for residue processing are normally designed with the objective of maximizing residue conversion. Downstream reactors are then used to treat the liquid products for sulfur and nitrogen removal. Examples of the slurry process are the Weber combi cracking and Canmet process. Conversion of residual feed takes place in the liquid phase in a slurry reactor. After separation the residue from the products, they are further hydrotreated in a fixed bed reactor containing an HDS catalyst. A chip 1-through catalyst is used which ends up in the residue. So this is the Weber combi cracking process. So feed and the catalyst they will go to the heaters. They are sent to the slurry crackers. The slurry reactor is maintained around 700 to 740 Kelvin and at very high pressure of 150 to 300 bar. Then it is sent to the high pressure separator where the product which is formed in the reactor that will be separated. Then low pressure separator. So they will go through the again fixed bed reactor and the product which we can get after the fractionation. Whereas low pressure Separator will separate the low fraction and that can be recycled back. So hydrogen which is not reacted, it will be recycled back, and the product which is formed, that we can take out, and the residue which is generated here we can send back for the further process. And treatment of the refinery gases. So as we have seen the many gases that form in the refinery, so these gases not only cause the environmental cause, also they are not useful in the reaction, and also they are not the part of the refinery. So these gases need to be removed. So generally the major gas which form is the hydrogen sulfide. So removal of hydrogen sulfide from gases is usually performed by adsorption in the liquid phase. The concentrated hydrogen sulfide is frequently converted to elemental sulfur by the Claus process, which is partial oxidation of sulfur hydrogen sulfide. In the Claus process, 95 to 97% of the H2S is converted. H2S is often removed with solvent that can be regenerated, usually alkaline amines like monoethylenamine. These amines are highly water soluble with low volatility, and their interaction with hydrogen sulfide is much faster than with carbon dioxide, so that the amount of absorbed CO2 can be limited by selecting appropriate condition. So this is the flow scheme for hydrogen sulfide removal by amine absorption. So fluid with catalyst, when goes to the slurry, then it will give the products. So it is separated to the hydrogen, the high pressure and the low pressure. So after that one, which is the H2S is formed, so that can be separated by monoethylenamine. So it is not shown in the flow diagram, but the H2S which is formed after the off gases, it will pass through the monoethylenamine where hydrogen sulfide will be solubilized, and that can be removed. In force claim of a typical Claus process, so acid gas which contains mainly the sulfur containing gases, so the temperature is around 1300 Kelvin, then it is sent to the boiler filled water, where the water will be heated and converted to the high pressure steam, and the acid gas will be cooled. So generally this is done in waste heat boiler recovery, WHBR. Then low pressure steam which is sent again, which is also formed by the further removal of the acid gas stream, when it is sent to the reactor, and after various stages the sulfur pit where the H2S is oxidized. So when H2S oxidized, then what we get is the water and sulfur. So that sulfur is taken into the sulfur pit. So condensers, they are kept in to cool it because of the exothermic action of the reaction. So H2S to SO2 ratio is maintained around 2 to 1. The gases which are formed, they will be sent out, and sulfur which is formed at is collected as the liquid sulfur. So these are the references to refer, and the next industry that we will discuss will be the plastic and polymer industry.